Hi friends, so last couple of videos we had seen what's a linear regression is like and what it is to build a model, put it into Azure, build web services, and also deploy a web service in the form of an R function. Those were all good handy informations. Now we move on from a linear regression to logistic regression. I have with me the famous Titanic data set. Those of you who are unfamiliar, I would just say this is a simple data set from the sinking of the Titanic and it's about the passengers who were on board, and it has the data like the information of the class of the passengers. Okay, let me put a filter here. It has information about the class of the passengers traveling, which is 1, 2 and 3, and then we have the gender, their age, if they were traveling with these siblings, and the number of parents they were traveling with and embarked from. And what we have is survival data. So how many of them survived the Titanic disaster and how many of them were unfortunate. So this is the kind of data. Now what we are trying to achieve here is, through the model, we are trying to understand, given these parameters as inputs, about their class, gender, age, siblings, parents, and embarked from, whether we are able to predict the survival of a particular passenger. Now so far what we have seen in linear regression is we were predicting a number, let's say the salary that we were predicting, or the sales based on the advertisement. These were the data sets that we had seen so far in the examples for linear regression. Now here what we are trying to predict is, actually we are trying to classify. It's a dichotomous output. So our regressant and the regressors, if we were to determine our regressant is dichotomous, that is, it's either survived or died. So and our input independent variables are either factored or continuous. So having seen all of these, now our y becomes dichotomous. So we are trying to classify here. So and while for linear regression we had said that it would be continuous in nature. So why not linear regression for this kind of data? That answers we can answer that, because simple linear regression is one with continuous variable evaluating the another, and what we are trying to know is the coefficients based on which we can determine the dependent, that is the regressant. Same is for linear regression, multiple linear regression, or the only difference is we have multiple dependent variables which independent variables which determine one dependent. Now logistic regression, if you would, is actually dichotomous in nature. So what we are trying to say is the dependent variable ranges between 0 and 1. It predicts. So what we are trying to predict is the survival of, or let's say we are trying to predict whether a person will get diseased or not, or whether a male is a spam or a ham. So where we have dichotomous output or regression, we would have to use a logistic regression. So I hope that makes it clear why we are trying to use a logistic regression here. Now some of a conceptual background, I will jump here and tell you. Link logit function, there was a mathematician, American mathematician, David Cox. He found a relationship between the log logit with the linear, I would say the linear independent variable. So what we are trying to say is, in P is the probability of an event. So let's say the probability of a person's survival is P. In that case we can link a log of probability 1 minus P in this equation, and we can fit it to the independent variables. Beta naught is the intercept, and beta 1 x1 can be our independent variables, that is our class, sex, age, siblings, parents, and embarked. So these becomes our x1s, x2s, and so on, and survive becomes the probability of survival becomes P. So if we were to take this formula ahead, what we are trying to find is the link logic is essentially we are trying to find P. So if you see the relationship here, it gives you this equation basically gives you the probability of occurrence of or its survival. So if you were to fit this into a model, what we will get is a value of P, and that is what we are interested in. On the basis of the intercepts and the coefficient and the x1s and so on, we will try to find out the probability of survival. I hope we have and the curve is called the sigmoid function curve, which ranges the whole idea is and the advantage is it ranges between 0 to 1. So we and the probability that we are trying to find for the survival would be ranging between 0 and 1. Now having said that, we move on and we jump onto R and try and build a model out of this data set. So I'll go step by step and we will see for this particular data set if we can find out and how well we can find out the logistic regression and hence predict the survival. So let's start with putting some of the data. So we get the data and we have the data in the data set. We are trying to clean it up. Okay, so what we are trying to do is I have studied the data and I know there are some of the values are blank for embarked and that of age. I could have I could have also as well got the mean age and imputed that, but I have chosen to ignore the records. So in these two lines of code, what I'm trying to do is I'm trying to do away with all those records which are blank or NA for embarked and age. And here what I'm trying to do is I know these are not relevant attributes, so I am removing them from my data set, that is ticket, cabin, passenger ID, name and fare. And I know these are not dependent, these would not determine the survival of a particular passenger. So now having said that, what is my data set looking like? We will take a look at that quickly. So my final data set looks like I have survived class, sex, age and siblings, parents and embarked, and I know these are the ones which are actually determining my survival. So and I move on. The next important part is to sample the model and use the sample the model and split the data set between train and test. So what I am trying to do is out of the total of 712 records, I am sampling them between train and test. I would use 500 of them to train my model and the remaining 212 to test it. So I am initializing a random seed, and then so this code would actually generate numbers greater than and equal to 2 randomly, and then I sample them up and then I split my training and test data set. So now if we were to quickly see the counts of our train and test data sets, so we have 500 in our training and we have about 202 for our tests. Seems all good. Next what we do is we model the logistic regression. So what we are saying for the data set training, we are going to use survived as our dependent variable and the rest of them as are independent, and we are using the family binomial link logit. When we specify this, essentially what we are trying to do is, and we are using the GLM formula, which means we are trying to use logistic regression and see the results. So we create a model log and then we try to see the summary of the model. So essentially now what we are achieving is we get the intercept, as I had explained, similar to linear regression, and we get the coefficients for each of them. Now we get a value of sex male, 6 we have male and females. Now if you see, interestingly, you find that for a male the chances of survival overall decreases, and decreases by the coefficient of minus 2.48. Similarly, there are two factors. I mean, the value for embarked, we have Q, S, and there were 3 of them. So if you see, there are C, Q, and S. So we get 3 values. Actually, if you go back, you see the value for Q, S, and C is the benchmark. So basically, if there is C, you would put a 0, and you would not consider that variable. Now if you were to employ that in the formulae, if you go back, you would see this is the formulae where you would impute, or where you will put your values in terms of intercepts and in terms of the coefficients for, and then bring out the probability of survival. So that's how we would read it. The next is the AIC. AIC is the fit of the model. So it doesn't mean anything as such for this particular model, but if you are having different kind of attributes as an input and you want to know which is the one giving the best suited and best fitted model, you would consider the one which has the lower AIC. So that's all this means. Next we move on is for testing the model. So we are trying to pass the result to the test data set. So this is the model that we have basically trained, and we are going to pass our test data and then check for the responses. Okay, so we have done that. Now what we are trying to see is, if you see, interestingly, what you get is for the 212 odd records, what you get is number ranging between 0 and 1. So these, if you see, all of them, they are actually the probabilities, but we are not interested in the probabilities. Our dependent or regressant is actually a value 0 and 1, and it is distinct in nature, and that is what we want. We do not want a probability. So if you see, what we are going to say is, if the result is greater than 0.5, we will consider the person as survived, and if it is less than 0.5, we would say the person would not survive. So this 0.5 is actually a threshold which we are considering, and which we have devised based on our studies or whatever. So basically, this is a threshold that we are going to pass on, and then get the output of the survival. So now if you see results, it would only be between zeros and ones. So understand something very clearly. In logistic regression, it is a classification problem, and essentially we are trying to classify one from another. Hence your decision boundary overall would be a straight line, because we are trying to although you will get a probability or a sigmoid curve, your decision boundary is not the sigmoid curve, and it doesn't range between 0 and 1. It is actually a straight line, because it differentiates one class from another, and that's all logistic regression is about. So we have done that. Now we would want to know the model accuracy. So the next two lines are actually going to just check the mean of the survive for those not survived, and we would just try to draw the model accuracy. If you see, based on the predictions, I am able to say my model is about 82% consistent. So these code basically just try to bring out the test of the model based on the test data which we had actually carved out from the whole data set. The next important part is the confusion matrix. So if you see here, what we have done is we have drawn a table for test survived. We have from the test data set, we have the survived attribute, and then we have the results that we got from the model. Now if you are going to study this, it is very interesting, and this is the confusion matrix. So what it means is the true positives and the false positives, and the true negatives and the true positives, negatives. So basically what we are trying to say is what is the diagonals, that is the 0 0, are the ones which are right. So basically I know that in the data set, in the data set there were 94 of them who did not survive the Titanic disaster, and my model predicted 94 of them correctly, that they did not survive, while there were 80 of them who survived, and the model predicted them to have survived. But for the other diagonal that you see, the model predicted them to have not survived, but they had actually survived. So this is an error, and at the same time the model had predicted this value to have survived, but they actually did not survive the Titanic disaster. So that's all this confusion matrix is about. But be very clear that this predicts the accuracy of the data, and you would understand how consistent your model is. And you want to decrease, you want to increase your diagonals and decrease your false positives. So that's all this confusion matrix says, and you can study this. The other important test is the accuracy test, that is the ROC curve that I will draw out. So this ROC curve is this one. So it gives you the receiver operating characteristics, or the area under ROC. Now what this curve is all about, for each of the points it basically brings out the ROC curve, and our ROC curve is all about the sensitivity and the specificity. So the x-axis here is about the specific model, how specific this model is. It is 1 minus specificity, and the y-axis is your sensitivity. Now listen very carefully. What I'm trying to say is, for this model, if this model were a very high classifying model, and it was able to discriminate all the classes of survived to the non-survived ones consistently 100% of the times, you would have a value 1. You would have a very high sensitivity and a very high specificity, which means I am again telling you, my y-axis is sensitivity, my x-axis is 1 minus specificity. So it's specificity. So in the case that I have a high sensitivity and a high specificity, this becomes 1 minus 1, this becomes a 0. This becomes a 0. So in that case, when this becomes a 0, your graph will look something like this. The value will be somewhere here on the leftmost tip. In that case, you would see the accuracy of your model to be almost 1. That means it's 100%. That's a very high classifying model. On the other hand, if you were having a model which is not highly sensitive and specific, in that case you would have it on the 45 degrees. So the area under this is actually, the more deep this area, the better your model is. And how would you determine the accuracy of your model is actually at the tip of your left. So this point here that you can see is the highest sensitivity and the highest specificity that this model can predict. So it's somewhere about 82 odd percent that we had seen. I hope the ROC curve is clear now, and that's all this was about. Next, what we are trying to do is, at the end of it, now we've built a model, we've tested its accuracy, and we have also classified the problem. Now we are trying to draw a function. The function takes the input data and it takes the threshold value. Let's say we have used 0.5 as a threshold value, but for, let's say, anomaly detection or fraud detection or credit card bill or let's say a fraudulent transaction, whatever be the case that you want to determine from the logistic regression, you say that 0.5 is not good enough for me. I only consider it if it is 95% consistent. So in that case, I create a function for the same model and then take it as an input. This table, let's try to print it for 0.5. This function is printing fair enough. Let's try to draw two tables and see how consistent it is. So with 0.5% as a threshold input, this is the kind of result that I'm getting, while with 0.75 this is the kind of result I'm getting. So it depends basically what is the threshold that you are interested in and what is your classification criteria based on which you will consider the person to have survived or not survived. So I hope all of this kind of makes sense, and you will be able to now understand logistic regression quite clearly, and implement that as a classifier or determining the dichotomous variables class. That's all this video was all about. And the next, in the last video I had already shared how to create the function and put it into Azure Machine Learning as a web service, and then help to determine the result in the form of a web service. So if I put this function on and publish it on Azure ML, I should be able to draw the classification in the form of a web service, and then get the results out of it in the form of zeros and ones. I hope this was helpful, and we will take this same data set into the next video, and we will be using the same data set to create a logistic regression model onto Azure ML. We have seen this in R, we will see it in Azure ML, how well we can do that. Thank you so much, folks. Stay tuned for the next video. Thank you.